All right, sounds great.
Hello, let's bring your screen over. So, hello there. This is our Gen Chem Study Session 3, hosted by Dr. Stephanie Taylor and hosted by our Living Learning Communities. As a reminder, these sessions are being recorded and they will also be uploaded onto our YouTube page. In the description of the event itself should be a link to our link tree for our next session, which is happening on December 1st, which is also a Monday, same time, as well as all previous recordings from this semester and past semesters for all of our Gen Chem recordings. So without further ado, I'll hand the floor over to Dr. Stephanie Taylor to start the session.
Thank you so much. Thank you so much. All right, so some general some general reminders. So we do have exam 3. Oops, where's my drawing tools? There we go. So exam 3 is on Saturday. So still Saturday, still at 10 a.m., still in the same rooms. I do need to send out those room assignments again, but they're the same ones as before. So you can always scroll back. So one of my favorite tricks sometimes is to hit the announcements tab and to just scroll back through all of the announcements. I know it's kind of boring, but somewhere in there is usually going to be all of the room assignments. They're in there somewhere. Um, but regardless, there is, so same rooms as before, still 10 o'clock in the morning. And November 1st, but it's this Saturday. I don't know about anybody else, but definitely it's the first day of the month. And so my brain is having some problems remembering, but it is in fact this coming Saturday. I also pulled this information on the left, which is what the exam covers. So this is also something Dr. Diekman posted on Friday. So chapter 7, so this is all the electron domain geometries, molecular geometries, hybridization. Section 12.2 down here is properties of liquids. So those intermolecular forces went really nicely into properties of liquids. Since we can do all of those electron domain geometries, please realize that that also means that nomenclature can also be tested on, as well as Lewis structures. So we'll do some examples, but one of the tricky parts here is that you can absolutely have something where you have to start from nomenclature, then draw the Lewis structure, and then tell me about the electron domains or the electron domain geometries or hybridization, or all of these things go together really, really nicely. Then chapter 8, it has the actual textbook sections 8.1, 8.3, and 8.4. I usually think of chapter 8 as being 4 real topics, which is balancing chemical reactions, and in addition to balancing chemical reactions, we can do, it's called stoichiometry, but grams, moles with chemical reactions. The fancy name for that, by the way, is stoichiometry. So it has a fancy name, but it's grams to moles conversions with chemical reactions. Limiting reactant, which I know they covered in lab last week, and percent yield. So those are the 4 things that are out of chapter 8. So I don't know about the other classes, but in general, we do ask probably a few more questions out of chapter 7, just because there is more stuff in chapter 7. If I tried to make you a topics list for chapter 7, it would be much longer than this. And even just talking about electron domain geometries, there's a fair amount that goes into all of that. So there's a lot of stuff in there. But so this idea of what's included, what's excluded is stuff that Dr. Diekman did go ahead and send out in the 701 section on Friday to kind of help you guys out with that. I did ask my class for some questions, so I did want to talk about some of the ones from them, just because all of them asked good questions. Some of them repeated a bit, which is understandable when you ask a large group of people. You'll get a variety of things that hit on the same topic. So I did not actually filter these super well, but um, we'll just see what we can get through. And we will always take live questions as well. But this one I did at least want to address, does the exam review cover all topics on the exam? No. Because basically I answer questions that are asked, and I don't actually start with the exam and go through just all the things on the exam. This is for a couple of reasons. One, the exam covers basically all of the material that we've been doing for the past 2 weeks, as well as the material we're going to do this week. I can't personally cover all of that information in 2 hours. It's just not possible. There's a reason why it takes like 3 weeks to cover everything, and that number of hours associated with it. Then the other thing is that, especially as I'm starting like this list of a lot of questions, I will get focused on helping you understand things that we either did before or things that are coming up, and so then it's not a comprehensive list by a stretch of the imagination. But I did get asked a fair number of questions, especially about things like limiting reactant, which is one of the last things that we actually wind up doing. So because there's really chapter 7 questions and there's chapter 8 questions, I was actually tempted to get into some of the chapter 8 stuff just to be a little bit different. Also, since the lab covered limiting reactant, that might help. One of the other things though, before I start doing chemistry stuff, I did actually see a number of folks tell me either things, so general, I saw things like I'm scared, I saw things like I'm lost, I saw a variety of things like this. So one of the things I did want to mention before we do anything else are some of the tools to help. So there are always things like office hours, there's always things like exam reviews, but in general, if you feel like you just don't even know where to start, this one is where I would recommend something like office hours. Because one of the hard things is when you get to that point and you're like, I don't even know what to do. Sometimes having somebody who's gone before gone before you, so either an instructor or one of the TAs, SIs can do this sometimes too, PLTL leaders, to kind of guide you through like where to start, can be really helpful. The other thing that can be helpful are things like the workshops, and trying to get kind of a grip on what's going on there. Or even we've got Alex assignments, and granted, maybe the Alex assignments don't make any sense. That's definitely a possibility. But if that's true, then you might take one of the Alex questions to things like either peer tutoring, which is in the basement of the library, or we also have the chemistry clinic. So we have two different resources on campus that they just have students hanging out waiting for you to ask questions. Um, so those are two different things. The chemistry clinic is in Berkner. Um, Technically it's the third floor, but it's actually just up one floor from the ground floor. The peer tutoring center is in the basement of the library. So there are different ways to kind of help get your feet back under you, for some of this content. It also can be a lot because there is that idea that we can start with a lot of stuff from the previous exam too and move forward from there. So there is a lot of stuff, that we can definitely do from previous times and move forward. So if it feels like a lot, that often is accurate because of the fact that when we went from exam 1 to exam 2, there's a lot of things we just left behind. And we were like, yeah, we're over it. We're done. No more. We won't worry about wavelength and frequency until the final. You're fine. But the hard thing is from exam 2 to exam 3, we kept pretty much all of it. There's a couple of things that we left behind, um, but very little did we actually leave behind in exam 2. So it's very understandable. So there's different ways to try to help get your feet back under you. Okay, So before I start answering miscellaneous questions, is there anything out of the chat that we would that has already popped out?
I currently do not see anything in our Q&A,
Okay,
so I think you're free to go, but as questions pop up the next time you're ready to ask, I will get them ready for you.
fabulous, fabulous. Okay. Oh, I like this question before I forget. Um, like I said, I didn't actually have time. I did not give myself enough time to organize these. But I had this question, are the questions going to be like the fall 24 exam, like covering the same content? Um, this this is more or less yes. Um, and this is the reason why it says more or less. So the way that we write exams in general is we usually write something like 20, no, we write more of the questions than that. It's like we don't write 28 questions. So we write somewhere between like 30 to 35 questions. Um, and then we ask 28 to 30. So the thing is that we always write more questions than we test on. So the reasons why it's similar content, but it's not the same content, is because we throw out different things depending on time, or depending on how well the question's worded, or depending on how close the questions are to each other. So there's always a discrepancy in there. So there are some topics that like we will definitely test on, but other topics that may or may not be tested on. So for example, we will test you on hybridization. So hybridization is the one that relates especially to things like electron domains. And hybridization is the one where we could think about this as having kind of like a chart kind of a thing. And if I have two electron domains, we call that sp hybridized. And if I had three electron domains, we call that sp2 hybridized. And if I had four electron domains, we call that sp3 hybridized. And five electron domains is sp3d, and six electron domains is sp3d2. Now, that connection that's just count electron domains and spit back out a hybridization, we will definitely do that. There's different ways to do it, but we will definitely do that. So that's I promise you, there will be a question that just says either here's a central atom or here's a line skeletal diagram. Tell me the hybridization. Go. The question though that might be on the exam, but might not be on the exam, and I don't know, has something to do with hybridization more conceptually. I'm just gonna call that hybridization in words. Um, and hybridization in words could be something like for the structure. So we'll do this both ways. So here's ammonia. So first of all, if I want to talk about the hybridization of the central atom, which is the nitrogen, then I'm going to count the number of electron domains. So here's one electron domain of the lone pair. Here's one for a single bond, one for the single bond, and one for the single bond. So when I'm talking about electron domains, this has four electron domains. Each bond counts as one, the lone pair counts as one. So there's four electron domains. If all I want to know is the hybridization of the nitrogen atom, four electron domains is sp3 hybridized. So there might very well be a question that just asks you for the hybridization on the nitrogen atom, and we would be done. It would be sp3 hybridized. We would be finished with the question. We move on with our lives. But it could also be something that asks something like, which of the following are true? And that's a question that we don't always ask, but sometimes we do. So now is the part where I try to write some sentences about this. Um, so I'm just going to write true statements because coming up with good false statements can be tough off the top of my head. And I'll make these bigger right now. It's like, I'll make this bigger in a minute. Wait, no, I'll make this bigger right now. Um, the lone pair on the nitrogen is also in hybrid orbitals. Um, I should say in an hybrid orbital. There's just one of them. As we already said, the nitrogen atom is sp3 hybridized. Each hydrogen atom, atoms s orbital overlaps with the large lobe of the sp of the hybridized orbital. There are 4 hybrid orbitals in this molecule. So there's 4 statements. So let's basically walk through how each one of these is or should be a true statement. So the first one says the lone pair on the nitrogen is also in a hybrid orbital. That is true. So when you look at nitrogen and the fact that it has these 4 sp3 hybrid orbitals, it does actually have a lone pair that goes into one. The lone pair counted as an electron domain. And that lone pair is also in hybrid orbitals. So since it counts as an electron domain, that lone pair still needs that same geometry, still needs that same bond angle, well, not bond angle, but still needs that same distance away from everything else. So that lone pair still belongs in hybrid orbitals. We already counted that the nitrogen is sp3 hybridized, 4 electron domains, sp3 hybridized. The hydrogen atoms orbitals are overlapping. So the hydrogen is one of the atoms that, because poor little hydrogen just has that little 1 electron in 1 s, hydrogen is basically never hybridized as a hydrogen atom because it only needs to overlap 1 little electron. That's all it's got. So hydrogen is just going to bring an s orbital. This is an s. What is that? So hydrogen is just going to bring its 1 electron in an s orbital. But when you talk about hybrid orbitals, one of the questions I got a bit was about things like the orbital shape. And really the only thing that's useful, there's different things, but the main thing that's useful about a hybrid orbital shape is the fact that this dot right here is going to be the nucleus of the nitrogen atom. And so when I'm trying to talk about how hydrogen is going to interact with this, what we can expect is this s orbital is going to overlap with the hybrid orbital. And since my hybrid orbital, which is this thing in black, hybrid orbitals do have 1/2 essentially that is a larger part of the orbital than the other. And the expectation is that there's a better likelihood that the electron from the nitrogen goes towards the hydrogen. So my nitrogen is over here, my hydrogen is over here. The little hydrogen electron is hanging out, but that nitrogen electron should be more likely to hang out close to the hydrogen as opposed to on this other side. So you see a larger lobe towards the hydrogen than not towards the hydrogen. So that is why we talk about the shape of the hybrid orbital, is to try to emphasize the fact that that electron should be in the bond. The part of the reason for hybrid orbitals is to emphasize how they bond and to emphasize how bonding works in covalent molecules. So that lobe should be larger towards the hydrogen. Oh, there are 4 hybrid orbitals in this molecule. That goes back to essentially what we were saying before, both that sp3 hybridization, that does give you 4 hybrid orbitals, and it also goes to the fact that your hydrogens are not hybridized. So when we start to talk about what can you expect to see on the exam, The hard thing is that I promise we'll have something where it's like, here's a molecule, tell me the hybridization, or something about what is the hybridization of the central atom. And your answer choices will be sp, sp2, sp3, sp3d, sp3d2. There are 5 hybridizations. There are 5 multiple choice options. That works out really well. And I think I'm the only person who's mean enough to make up fake hybridizations. I could be wrong, but every once in a while, if you see an old exam and you see some hybridizations that don't actually exist, that's my fault. Um, because I will do that. I will make up hybridizations that look good but are fake. Um, and I didn't write the hybridization question. Um, so, oh, but this one where we were talking about hybridization in words, I don't know. We usually write at least one question that's got hybridization in words, but will it make it to the exam? I don't know. That just sometimes it does and sometimes it doesn't. Okay, so I was going to go ahead and take a look at things like balancing chemical reactions and actually a little bit on limiting reactant. So what I am going to do for limiting reactant. So first of all, I get to pick, um, everybody loves this one, or maybe not. Um, so these are all gases, first of all. Gases, gases. So this is nitrogen gas and hydrogen gas makes ammonia gas. When we look at this, first of all, I am going to balance it because I wrote it from scratch, so I have to balance it. One of the other things on the exam that I will tell you, so if you see something that looks like this, and by looks like this, I mean there are no coefficients. If you see something with no coefficients, everything looks like it's 1, you need to check if it's balanced. So if you don't see anything, if you see no coefficients in there, you need to check to see if it's balanced. So I've got 2 nitrogens on one side, but only 1 on the other side. Oh, this is not balanced. So I'm going to go ahead and balance this. So there's 2 nitrogens here. I need 2 here. Now my hydrogens, I've got 2 on one side and 6 on the other. So I need to put a 3 in there. So now my reaction's balanced. So the thing is, if this reaction is what you saw, if there are coefficients, then you can trust that we balanced it properly. So one of the weird things, so we will not give you coefficients, but give you wrong coefficients. So basically we'll omit information, like we want, well, sometimes we'll give you a chemical reaction, but there's no numbers in front. And so you do need to balance it in that case, and you need to check, because sometimes we just leave them off there and we expect you to check. But if there are coefficients, then you just trust them. So you don't have to double check to make sure that we balanced it correctly. If you see coefficients in a chemical reaction, you can trust that they're balanced. So now that I know that I've got the same number of nitrogen atoms on both sides and the same number of hydrogen atoms on both sides, that is a balancing chemical reactions. That is something that you will need to be able to do for the exam on Saturday. There are 2 kinds of well, 3. We'll do one of each. So there are 3 kinds of calculation questions that can come up with chemical reactions. So one of them is something like, given 5 grams of nitrogen gas. Oh, make it big, make it big, make it big. Okay. So granted, this is supposed to be with this same balanced chemical equation. So I will go ahead and grab this again. I'll bring it down here. So here's my balanced chemical reaction. It says, given 5 grams of nitrogen gas and an excess of hydrogen, how much ammonia can be produced? I should put that in grams. How much ammonia can be produced in grams? So when it looks like this, what I want you to notice is that it actually told me that there's an excess of hydrogen. So when something says excess, that means basically too much. That means all we need and more. So that is an option. So when we talk about limiting reactant, this is not a limiting reactant problem. So basically we told you then basically that nitrogen is limiting because we actually identified the excess reactant. So for those of you worried about limiting reactant, since it was in the lab last week, this is the kind of question that's actually not a limiting reactant question, because it basically already says which one is which. So without having to do any additional math, this actually tells you hydrogen's in excess, nitrogen is limiting. That being said, we still need to answer the question. So since this is in grams, your chemical reaction itself is always in moles. It's also technically in molecules. So it's either in moles or it's in molecules, but it's never in grams. Which means we have to do some math here. So I know that we're starting with 5 grams of nitrogen. And then, so what I'm going to do is I'm going to start with my 5 grams of nitrogen. And then what I need to do is I need to go to moles of nitrogen so that I can use my balanced chemical equation, so that I can use my reaction. And then I'm going to go to moles of ammonia. And then I'm going to go to grams of ammonia. So this looks like a lot of arrows, just in part because it is. So I'm going to start off with grams of nitrogen, then move to moles of nitrogen, use my reaction to go to moles of ammonia, then grams of ammonia. If I'm going to go from grams to moles, I'm going to need a periodic table. I really would have thought I would have figured this out by now. Hey, there's a periodic table. Yay! So I'm going to put this periodic table over here. So nitrogen is 14.01. There are 2 of them, so 14.01 times 2 means that for this 5 grams of nitrogen, since there are 2 nitrogens, there are 28.02 grams of nitrogen in 1 mole. From there, I have moles of nitrogen, so that's what I need. Now it says to go to my reaction. When I look at my reaction, what I care about is I care about my nitrogen going to my ammonia. So I'm going from one to the other. What I can see here is I can look at the coefficients. So there's 1 nitrogen to every 2 ammonia, and that is something in moles, also in molecules. So the idea is I can look at my chemical equation and say I have 1 mole of nitrogen, and when I have 1 mole of nitrogen, I actually make 2 moles of ammonia. So this is the thing that comes out of my chemical reaction. So that's why I need my chemical reaction, is because that's going to tell me essentially how to go in between two different things, how to go in between two different substances. Because everything that we've done before now was dealing with atoms, where you would stay with like atoms of iron and you go to atoms of iron. We could do molecules, and we could talk about molecules of ammonia and stay with molecules of ammonia. But now we're going to go in between substances, start with nitrogen, wind up with ammonia. So we are actually using stuff from the chemical reaction itself. So then I'm going to say that there is 1 mole of nitrogen. And you get 2 moles of ammonia. Then from here, now I have moles of ammonia. If this is where I stopped, I would have moles of ammonia. So that means I need to go to grams, because that's what the question asked me for. So in 1 mole of ammonia, I need to figure out how many grams of ammonia I would have. So I'm back to my periodic table. So I'm back to that idea that nitrogen has an atomic mass of 14.01. There are 3 hydrogens, so you need to take 3 times 1.008. You do not have to have that memorized, but it is the number that's right there. So we wind up with a total of 17.034. So I went from the given number of grams. I'm going to divide by my molar mass. So anytime that we're in grams and we're going to moles, grams is always going to be the larger number. So we're dividing to go to moles. Then we have to use our mole to mole ratio. So that's what that 2:1 is. We got that from our balanced chemical reaction. And finally, we're going to multiply by our grams again, because we went from grams to moles, back to grams. So when we're all said and done, I get 6.08 grams. It's probably more sig figs than I need. 6.1 grams. I'm going to take just a moment. Oh, no, I can't. I was going to shut my office door because I can. That's what the AirPods are for. You can't hear that, just me. So this is an example of one kind of calculation that we could potentially do for the exam. Now, one other thing to keep in mind. So this went grams to moles to moles to grams, has all the conversion pieces in it. I could just as easily write a question that instead of telling you that this is 5 grams of nitrogen, I could also make this 5 moles of nitrogen. So realize that we can have you start in grams. We could also have you start in moles. So we have options in there for what sorts of questions we ask and where you begin and where you end. If this question is in moles, this question actually becomes much shorter. Instead of 5, let me make that a different number. Let me make that like 27. So let's take the exact same question. I'm either going to copy and paste it. And instead of grams, we're going to make this 27 moles. So if the question looks like this, I will just write this out again. Nitrogen plus, we already balanced it, goes to. So if we start with moles of nitrogen gas, so I have 27 moles of N2, I still have to go and use my balanced chemical reaction. So this thing I still need to use. So the fact that I still have 1 mole to 2 moles, I'm still going to use that part. So 1 mole of nitrogen for every 2 moles of ammonia. But the thing is, that's in moles. So that's all I have to do. So if you already have moles and that's all you need, you don't need grams. So your balanced chemical reaction is in moles. So if you already have moles, the calculation should actually be shorter. So sometimes we get really used to everything being in grams. So we see a lot of grams and we expect a lot of grams. But we often get on exams, give you guys a question that's all in moles to save yourself some time, because then you don't need any of the molar masses. You just don't have to worry about them. The other thing we will do in here is we will sometimes go ahead and give you the molar masses. Sometimes they'll say molar mass, and this would be 20.02 grams per mole. And then ammonia, and we give you guys the molar mass of this one. Molar mass, this was the 17 point, I used it, 034. Now, this is the other time where I tell you the truth. So just like I was explaining how that we write exams, and when we write exams, we don't always know like which ones we're cutting and which ones we're keeping until kind of the very, very end. Like we're gonna have that conversation like later tonight. The exam is on Saturday, so we've got like, what is that, 5 days, 6 days? And we're gonna make decisions about what we keep, what we cut this evening. One of the other things that sometimes happens is sometimes we intended the question to go from grams to moles, but at the last minute we decided that the questions are too long and we should save you guys some time, and therefore it should just all be in moles. So sometimes you have molar masses in questions, but you don't need it. Sometimes you don't have it and you do need it. And that is sometimes an artifact of us wanting to test you on knowing when you do and don't need molar masses. And other times it's actually an artifact of we changed the question 4 days before the exam and we didn't go back and take them out or put them in. So all of those things sometimes happen. Okay. I've been talking for about a half an hour. So I know we're not, I did a bad thing. I'm not on any particular half an hour, but I'd like to go ahead and double check and see what questions we have out of the chat to see if we've got any before I do too many more calculation questions. So do we have any questions out of the chat so far?
You have 4 questions currently. I'm going to start with the oldest one and work our way up.
Great.
So the first question you have is, please give us a review of VSEPR. It's spelled VSEPR, and polarity.
Okay.
The second question you have is, could you go over a step-by-step review in how to draw the line skeletal diagrams?
Okay.
The third question you have is, can you please go through intermolecular forces and boiling points? Thank you.
Okay.
The last question you have is, can you go over hybridization and the IMF?
Okay. Anything else right now?
That is all in chat right now.
Okay. Fabulous. Okay. Um, so I'm gonna go ahead and do one limiting reactant question. The reason why it sounds like I'm trying not to laugh, y'all, this is not exactly, but this is more or less an outline of the whole chapter of chapter 7. Um, so good list, good list. Um, hmm, um, I will do my best. I will absolutely do my best. So I'm going to go ahead and do um, one limiting reactant problem just to kind of show how that works, or show one of the ways that it works. Um, How do I want to do this? I am cheating. Yes, let us cheat. And let us save ourselves a little bit of time. And how many grams of hydrogen do I want? 10. No, 2. No, 5. The same number. Sorry. We're just going to do the same number of grams of nitrogen and hydrogen and see what this looks like. So in general, there are 3 different ways to do limiting reactant. Because this one specifically asks how much ammonia can be produced in grams, I'm going to show you the way that I think is actually the most common. It's actually not the way I usually teach it in class, but I think it makes a lot of sense for this question setup. Also, it is the way that technically we've already done some of the work for this. So this is still off of the same balanced chemical reaction where I have nitrogen and hydrogen going to ammonia. So I still have this exact same setup. And what we found earlier is we actually found that if I was to react all of my nitrogen with as much hydrogen as I could possibly need, I'd make 6.1 grams of ammonia. So that was the work that we already did earlier. So we looked at the 5 grams of nitrogen, did all of the math to look at how much ammonia it would possibly make. So essentially, we basically ask if we can use all the nitrogen, how much ammonia does that make? How much ammonia is made? And that's a question we actually already answered, which was 6.1 grams. Now we're going to go ahead and ask the question, since I have nitrogen and hydrogen, if we can use all the hydrogen, how much ammonia can be made? But this question we actually have to solve for, so we haven't done it yet. So I have 5 grams of hydrogen. So I'm going to take my 5 grams of hydrogen and I'm going to take my periodic table, which I left somewhere over here. And there's what, 1.008 times 2, because there's 2 atoms of hydrogen. So we're going to divide. 2.16. This is the reason why I keep a calculator next to me. And 1 mole of hydrogen. So we are going to, again, divide. And then because we're doing moles of hydrogen, but I want ammonia, I have to go to my balanced chemical reaction. So for every 3 moles of hydrogen, there are 2 moles of ammonia. So I'm going to use this mole to mole ratio out of the balanced chemical reaction. So there are 3 moles of hydrogen for every 2 moles of ammonia. And then we found earlier, because we already did this math, so that in 1 mole of ammonia, we get 17.034 grams. I am cheating because we did that earlier. I do consider it cheating sometimes when it's like, I could do a question from scratch, but based on the number of questions in the chat, I'm going to save a little bit of time. Divided by 3 times 2 times 17.034. And I get, as far as how much ammonia is made, I get a number of 28.2 grams. So the question now is, which one is true? So essentially, we calculated if I have 5 grams of nitrogen, but I could make 6 grams of ammonia, and I calculated if I had 5 grams of hydrogen, I could make 28.2 grams of ammonia. But only one of those is true. They're not both true. And this is the part where thinking about limiting reactant like a recipe can actually be really useful. So, for example, if I was going to make cupcakes, and you can do this with absolutely any recipe product that you want. So I don't care what it is. Um, but if I was going to make cupcakes and I only have like one egg, and we'll pretend that my recipe needs an egg, but I have like, I don't know, a room full of flour and sugar, just pounds and pounds and kilograms and kilograms of flour and sugar, then if you look at all the sugar we have and all the flour we have, if we have a lot of that, you're like, oh, we're gonna make a whole lot. And it's like, yes, but I have one egg. So the number of cupcakes you can make is going to depend on the thing you have the least of. So that's where, when we're looking for limiting reactant, whatever we can make the least amount of is going to be the correct answer. Because basically the hydrogen's like all optimistic and it's like, if we could use all the hydrogen, look how much we can make. And it's like, that's great, but we're going to run out of the other thing before we ever get there. So the question asks just how much ammonia can be produced in grams, and that answer is going to be that same 6.1 grams, because nitrogen here is the limiting reactant. But we only know that because we checked and we looked at how much ammonia can be made from nitrogen and how much ammonia can be made from hydrogen. So like I mentioned, so that does answer that limiting reactant question. Um, as you might imagine, there are different limiting reactant questions that can be asked. So we can also ask you just what the limiting reactant is, or we can ask you how much it's produced and what the limiting reactant is. So this could say 6.1 grams, nitrogen is limiting. We can also ask for things like excess reactants. So in that case, you have to tell me basically how much hydrogen is left over at the end. So there are different sorts of limiting reactant questions that we can do, but this at least gives you a little taste of what limiting reactant can look like. So a review of Vesper and polarity. So I'm not gonna lie, y'all, that took me a whole week. That took me 3 hours with all the questions, and I didn't actually cover all of it in that amount of time. So, but let's go ahead and take a look. So what I can do in this amount of time, where is the table I like so much? That's the table that I made. Where is the table I stuck in my notes? I like this one. Da, 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 da. So I did not make this, which is why it says from Dr. Paul McCord at UT Austin. He's got much better cartooning skills than me. So in general, here is this. Also, one of the other questions that I did see from my class a couple of times was something like, do we have to memorize all of this? Yes. Part of the reason why this took me so long is I spent time in class talking about where all of these names come from in the hopes that that would make some things make more sense. Talking about where some of these bond angles come from. Yes, you have to know all these words. You have to know all these angles, all of it. Yes. If it is on this page, yes, you have to know your electronic geometries, your molecular geometries, all of it. The bond angles, yes. So one of the things to note up here is there are electron domains. So when we have electron domains, the whole idea of VESPER, the whole idea of, let me highlight all of these first and then we'll spell that out. So I don't know why my voice is going because I can only talk for so many hours at a time. So when we do talk through this, so this is called valence shell electron pair repulsion. So that's where VESPER comes from. VSEPR. VESPER. VSEPR. Valence shell electron pair repulsion. And all that is supposed to mean is that electrons are negative. So since electrons are negative, electrons repel each other. So when we have a bunch of negative stuff, it pushes against the other things that are also negative, which is your other valence electrons. So that's how we get all of this. We do also have data to support this. So when we talk about the bond angles that are involved, those bond angles are things that we actually do have data on what those things actually are and look like. So valence shell electron pair repulsion, that is the reason why when we look at linear, why if you just have two electron domains, so for example, a carbon with two double bonds, why we talk about this bond angle here being 180 degrees. That's because this is linear. And sure, I can go ahead and make this carbon dioxide just so I draw a molecule. But basically what's happening is you've got 4 electrons in each of those double bonds, and they are trying to give themselves as much space as possible because you've got some negative stuff in one double bond and negative stuff in the other double bond. Electrons are negative, and they are trying to get as far apart as possible. So that's where that comes from. It makes a straight line. That's why we call it linear, 180 degrees to describe it. So that same general story of, and now they get as far apart as possible, and now we call it this thing, because that's kind of what it looks like, is how all of these work. So trigonal planar has 3 electron domains, and it is flat. So anytime you see the word planar, it shows up in a couple of places. So here's planar, and I know it's somewhere else, square. There's planar. So anytime you see planar, planar basically means flat, planar. This is a geometric plane. So not an airplane, but like a flat surface plane. We mean flat. It's in the plane. That's all there is. Flat. So that's why when you talk about trigonal planar, we're trying to draw something that has 120 degrees because it's flat. So it's like you took a circle and cut it into 3 pieces. Square planar, that's part of why this thing, you could actually just draw it with a central atom here in the middle, and why it just has the 90 degrees, because square planar is, again, perfectly flat. So I am not going to go over all of these shapes. So if there is a particular shape that you wanted more information on, I'm happy to go over a particular shape, but each one of these has their own story. The other thing I will point out, speaking of all of these having their own story, in the 701 section, one of the things that you'll have access to is this folder that says pre-recorded lecture videos. And in the pre-recorded lecture videos, you have a file that says chapter 7, and the chapter 7 link goes to OneDrive, and that has a whole thing on electron domain geometries, and a whole thing on molecular geometries, and a whole thing on VSEPR examples. So all of chapter 7 is available for you in a video format. I made these videos. So they are old, but the information in them is still the same. The electron domain geometries haven't changed. So those are all the same. They're all in there. They are available for you should you want those. So if you do just want everything from scratch, that is what those videos will do. So when it comes to looking at these and polarity, can I just paste it again, or will it make, yes, good. Okay. So when it comes to dealing with VSEPR and polarity, the thing is that polarity always asks about 2 questions. So polarity, you always have to assess 2 different questions. You need to assess the lone pairs, and you need to assess the bond angles. Or sorry, not bond angles, bonds. Polar or nonpolar? So if we just address the first one, lone pairs, here's the deal. Anything that only has one lone pair will be polar. So all of these are polar molecules. I don't promise you anything about the bonds right now, but all of these are polar molecules. Bent is also going to be a polar molecule no matter what. T-shaped is going to be a polar molecule no matter what. So everything I put a box around is a polar molecule because of the lone pairs. So this whole first line where there's just one lone pair on the central atom, those are all polar molecules because that lone pair doesn't have any other lone pair to possibly cancel it out. So that lone pair is like an extra negative set of electron density, and there's just nothing to counterbalance it. So everything with only one lone pair has to be a polar molecule. When you get into two, this is the part where the square planar one could be either way. So for example, I'm just going to use A's and X's. So I'm going to have 6 electron domains. I'm going to talk about these guys in just a minute. So we're just going to start off with these being hydrogens for now. So first of all, the lone pairs that I do have on the square planar geometry do cancel each other out. So this lone pair and this lone pair are exactly opposite. Lone pairs exactly opposite. And in this case, when I say exactly opposite, they are actually 180 degrees from each other. So they are one on top of the other, lone pairs. So the lone pairs do cancel. Then one of the questions I saw a fair amount from my classes is, what are we going to do about polar bonds since we don't give you guys the electronegativity scale? So what we're going to do about that is I have a general rule, which is non-polar bonds are either the same atom, so that could be a carbon to a carbon, that could be an oxygen to an oxygen, that could be a fluorine to a fluorine, I don't care. But non-polar bonds are the same atom, or carbon to hydrogen. These are the only two things that I consider to be a non-polar bond. Everything else, two different atoms. Not carbon to hydrogen. Carbon to hydrogen is defined as a non-polar bond. We are going to define all the other combinations as a polar bond. Yes, that is a simplification. That is technically an incorrect statement. But the purposes of this course is to get y'all to get a general idea of polarity. So we're not going to give you electronegativity values. You are supposed to look at the periodic table and have a general idea of where fluorine is, and therefore what atoms are more electronegative than others. Going back to my periodic table, where did you go, my friend? There you are. So fluorine is the most electronegative atom. As you get closer to fluorine, things get more electronegative in general. Well, yes, there are some pairs of atoms that are essentially nonpolar, even though they're different. Since you're not going to have electronegativity values to go off of, you're just going to assume if it's the same atom, it's nonpolar next to each other. or if it's carbon to hydrogen. Everything else you're just going to assume is different enough. It is an oversimplification. So it's not entirely true, but for the purposes of trying to figure out, is there some difference, is there not some difference? That's the general assumption you're going to make. So what I do have here, I got some mystical element that I didn't name, but everything around it is the same. So I'm going to assume that I have polar bonds. So these things that I'm drawing are dipole moments. So when you look at this, this is supposed to be a dipole or a dipole moment. This is supposed to be your positive end. Should perhaps write out the word positive. This is supposed to be the negative end. Because you're drawing a dipole because you have a difference in electronegativity. So usually we do this when we think about things like a hydrogen bonded to a fluorine. And we can draw the fact that the fluorine has both more lone pairs. The fluorine is also very electronegative. So I expect the hydrogen to have a partial positive charge, the fluorine to have a partial negative charge because there's more electron density on the fluorine. So I've got this molecule here. It has polar bonds. And I know I've got all these wedges and dashes, but if we looked at this a different way, so if I drew it where I had A, but then I just had, it really looks like this. Granted, there's, that's supposed to be a lone pair. Well, lone pair here, lone pair here. These are actually 180 degrees and 90 degrees from each other. So even though this looks more like a Lewis structure now than a three-dimensional drawing, my hydrogens are actually supposed to be 90 degrees from each other, because this is an octahedral geometry because of the lone pairs. So all of those hydrogen polar bonds actually cancel out. They run smack into each other. So this would be an example of something that has polar bonds, but is overall a non-polar molecule. And being able to evaluate polar bonds and the molecule overall are also things y'all should be able to do. Okay. That being said, if I drew a different one, so one of the other things we wind up with is occasionally this need to draw different things. So here's, yeah, we're gonna do this. So there are sometimes reasons where we will draw things for you. And I apologize for, you guys cannot hear me burp, but if you do hear me burp, I'm sorry. The goal was to not be hungry before the exam review. But I apologize. So here's the deal. We would have to draw these for you. So we draw these for you because you don't have enough chemistry language to draw these on your own. But what I want you to notice is here I've got fluorines, so I should expect some dipole moments going out towards fluorines. Here are also fluorines. These are both supposed to be variations on that octahedral geometry where I still have my square planar geometry. The thing is that in the blue version, my fluorines cancel. So in the blue version, the fluorines cancel. They're 180 degrees from each other. They're pulling in exactly opposite directions. Those fluorines cancel. In the red version on the left, the fluorines do not cancel. They're basically on one side of the molecule, and so part of the molecule is actually polar. So the red one is polar, the blue one is non-polar. So one of the things that happens with polarity is sometimes we actually have to draw the molecule for you because exactly where those individual atoms are plays a role in determining polarity itself. So one of the difficult things can be when you have the possibility for things to cancel out, how do you know? So if they are different, so if I have hydrogen and fluorines, like I do in this example, then you have to look at where they actually are. Can they possibly cancel out? Is that an option? So you do have to sometimes draw things out and consider, do they cancel? Because sometimes it'll also matter what that configuration looks like. Other times, though, if it's all the same, if I have all hydrogens or if I had all fluorines, then they actually, as long as they're all the same and the lone pairs cancel. So if the lone pairs cancel and you have polar bonds, but all the polar bonds are the same, then you can actually have a non-polar molecule with polar bonds. So the thing with polarity is practice helps. And polarity, you have to have that 3D viewpoint of things because that 3D viewpoint is going to play a role in how all these things work. Wedges and dashes. So I drew wedges and dashes here. Um, so the only reason why I like to draw wedges and dashes. You do not have to draw them. We are allowed to draw them. So the whole idea of wedges and dashes is a wedge is supposed to be coming out at you. Dashes are supposed to go behind the page. So hopefully this will be a helpful example. So if I have a molecule like carbon dioxide, but I just wanted to say, here's my carbon as a central atom, and then here is a thing here, and here is a thing here. This thing is linear, and right now it's just in the page. But if I wanted to try to draw this in wedges and dashes, it would look something like this, where I would say, here's my central atom, and then I have one thing coming out at you, and I have the other one going back into the page. So essentially, I took something that is supposed to be long and just in 2 dimensions. So I could take my pen, right? But then if I'm trying to say, aha, and now my pen comes out at you like this, that rotation involved is supposed to, the wedge is supposed to be coming out at you, the dash is supposed to be going back behind. That was the goal. So we are allowed to draw those. So they are things that we expect all of the instructors to have shown you at some point. So if all of the instructors have shown them to you, they're fair game to put in the exam, which basically means one of the things that happens. So while we can ask y'all to draw some structures from scratch, we can also just say, here is a picture of a molecule. Tell me what the electron domain geometry or tell me what the molecular geometry is. And at that point, you need to be familiar enough with what wedges and dashes are so that you can recognize it and at least not be intimidated by the use of wedges and dashes. So that's the real reason why I use them in class, is because that way, when you see them later on an exam or something, you've seen them before and you're like, oh, they're just trying to show me a 3D thing. That's what they're for. Some people find them more helpful than others, but at least if you know that wedges and dashes are just trying to show you shape, that's their goal, then that's usually helpful in knowing what they're being used for. Okay, so that was not all of Vesper and that was not all of polarity, but that was a general review of Vesper along with some polarity. So again, if you have specific questions about particular shapes that you really wanted, then I'm happy to go over that some more. But again, it's really easy to spend a lot of time on Vesper and polarity, at least for me. Step-by-step line skeletal drawings. Let's go ahead and look at step-by-step line skeletal drawings. Okay, so first of all, there's two different directions this goes in because it sounded like the person wanted to know how to draw them yourself. So first of all, you still don't get to draw circles, but something we could do. We could ask you to draw a line. Oh God, would I do this to you guys? I don't know. But sorry, there are times where I'm trying to mentally consider, like, would we actually ask you to draw this? The question was, how do you do this? So I'm just going to answer the question. So what the line skeletal drawing was asking, and let's go ahead and say that we gave you a formula that was structural. So let's say we asked you guys to draw the line skeletal diagram. We'll just go with this guy. Sure. Yeah. So this has 5 carbons. 1, 2, 3, 4, 5. So when we talk about carbons, that's 2 right there, because this is a carbon and this is a carbon, and this is a carbon and this is a carbon, and that is a carbon. This also, when you look at it, is all the hydrogens you possibly need to fill the octets. So we typically don't actually ask y'all to draw the line skeletal diagram only because only because trying to give you guys something that is a formula enough so that you can read it and then translate it into that is just not something that we typically do. But you can basically figure out, like, okay, I've got 5 carbons, they have all the hydrogens around them that they need, so there's no double bonds involved. And so that's 1, 2 carbons, so 2 carbons because I've got a line, and then 3 carbons for 5. But oftentimes the question is more trying to get at something that looks a little bit more complicated. Whoa, that's at a weird angle. One moment, please. There. I need nitrogen somewhere. So it's a nitrogen to a hydrogen, and I'm going to put double bond here, and and oxygen over there. By the way, you get really good at drawing hexagons in organic chemistry, so that's later. Yeah, it looks good. Okay. So here is a structure. And we can ask a variety of different things on it. But what I am going to do is just translate what on earth is happening here. So first of all, everywhere where there's a bend, so these are all bends, are carbons. There's a carbon over there and here and here. And there's also a carbon on the end right there. So all the blue dots are supposed to be carbons. So if I just redraw that part, I'm going to also draw the lines in there. So everywhere where there's 2 lines together, those are double bonds. So I do in fact have a carbon single bonded to a nitrogen with a single bond to a hydrogen, to a single bond with a carbon, to a single bond with a carbon, to a single bond with a carbon, with a triple bond, 1, 2, 3, to a carbon. Then this carbon is this carbon, a single bond to another carbon with a double bond to an oxygen, carbon, carbon double bond. There we go. So I'm not finished yet, but now I have my skeleton. My nitrogen gets a lone pair. Everything in group 5A gets one lone pair. My oxygens get two lone pairs. Everything in group 6A gets two lone pairs. The carbons don't get any lone pairs. This actually goes back to the fact that it has 4 valence electrons. Carbon's looking for all bonds. So starting over here, I've got a single bond and a double bond. So that does not have a complete octet, so it needs a hydrogen. This one has 2, 3, it needs a fourth. This carbon has 1, 2 single bonds, so it needs 2 more single bonds. This carbon's got a double bond and 2 singles, it's fine. The one that I circled has 3 single bonds, it needs a fourth. This one just to the right of the one with a circle around it has 2 single bonds, it needs 2 more. This one has a triple bond and a single bond, it doesn't need anything else. This one is just a triple bond, so it also has a hydrogen. So we do go ahead and complete the octets of carbon with hydrogen. Nitrogen and oxygen, we typically just need lone pairs. We'll draw the hydrogens that belong to the nitrogen, or we'll draw the hydrogens that belong to the oxygen. So this is basically translating that line skeletal diagram. And then we could ask different questions. So granted, we would have asked it on this guy. So let's go ahead and I'm going to point to atom to the nitrogen and ask you for the hybridization. I'm also going to put in this line and call this B and ask you for the bond angle on B. So the hybridization of the nitrogen. So if we're talking about the hybridization of that nitrogen, I know I already drew it once, but basically I like to take a look at the nitrogen and then just redraw that nitrogen. It's got a hydrogen and 2 single bonds and a lone pair. So when I look at the nitrogen, it's got 1, 2, 3, 4 electron domains. That means it is sp3 hybridized. And we could play that game with any atom on the diagram. So we could even point, it's a little harder to point to the one on the end, but we can point to the one on the end and be like, what's the hybridization of that? And that little guy is a carbon with a triple bond. Because of the triple bond, it should still have a carbon on the end. And we would call that one sp hybridized. So it's got 2 electron domains, a triple bond and a single bond that's sp hybridized. I also put this bond angle on B. That thing is all twirled around now. So the bond angle on B, that's a carbon with a double bond to an oxygen that has a lone pair, and then 2 single bonds. That bond angle, because of the oxygen and the lone pair, because of the double bond, that double bond is actually going to squish that angle. So this actually did ask for the bond angle in here, since the double bond is not part of that bond angle. This is going to be less than, and I do need to count the fact that this has 3 electron domains. That's trigonal planar, so that's 120 degrees. So that would be my bond angle B. So line skeletal diagrams, if the only thing you need is it points to a particular atom or it points to a particular spot, just redraw the thing that you need. Don't have to worry about the whole thing. But to give you some example, I went ahead and drew the whole thing, and somebody asked me about oxygen. So there's my oxygen with my 2 lone pairs. But yeah, basically it is just kind of a point to things and investigate whatever they're pointing at. If you don't need the whole molecule, don't redraw the whole molecule. For practice, when everything's calm, it can be nice. But that's the majority of how that one works. So we talked about how to draw step-by-step line skeletal drawings. So really, when it comes to step-by-step line skeletal drawings, I recommend practice. And what I would do for the steps is I would go ahead and basically add the carbon first. And then I'd go ahead and before I forgot, I would add lone pairs. 1 to nitrogen if you have any, 2 to oxygens if you have any. And then I would go ahead and add hydrogens to carbons to complete octets. So that's the order I would do things in. Add the carbons, add the lone pairs, add the hydrogens. And you can just scribble on the original diagram. So some of the shorthand notations I've seen that still work really well. Look something like this. So if this is my original structure, sometimes people will just go ahead and they'll be like, there's a C there, and a carbon 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 there. So that's step 1, add carbons. And then step 2 is the lone pairs. So here is the lone pairs on my oxygen. And then hydrogens. Oh no, I need a new color. Orange. And this is the part that does get a little bit quick. So I look at this carbon, it's got 1, 2, 3, so a double bond and a single. It gets a hydrogen. This carbon's got a double bond and a single, it gets 1. It's got 2 singles, it gets 2 more hydrogens. This one's got 1, 2, 3 single bonds, it needs 1 more. This one's got 2 singles, it gets 2 more. This one's got a single and a triple, it's done. This has a triple, so it gets 1 more. So that's the order I would actually go in. And so people will just go ahead and scribble on the original drawing to save themselves some time and not always redraw. So sometimes that can be helpful too. Okay, I've been talking for a while, so it's a good time to check in and see if there's other questions from the chat, especially if there's questions over the stuff that we've already gone over, even though I know I didn't finish the list we already made. So are there any questions in the chat so far to add to the list?
Yes, you have 4 questions currently. The next question is, can you go over percent yield and actual and theoretical yield?
Yeah, no problem.
Question 6 is, could you go over sigma/pi bonds and vapor pressures?
Okay.
The 7th question is, where could we find the electron domain/shape diagram you showed us?
Okay.
And the 8th question is, what sorts of questions will be asked about skeletal drawings?
Anything else?
That is all I have for now.
Okay. All right. So in general, so let me actually address what kind of questions can we ask about skeletal drawing. So there are, so I kind of showed off 2 of them, which was basically pointing and asking about hybridization, pointing and asking about a bond angle. So I did show off 2 kinds of questions. The kind of question I didn't show off was counting sigma and pi bonds. So that is the other thing that we can do, is ask you to count sigma and pi bonds. So that is the other thing to do. So, and the other thing I will state is I'm like, as I say this, one thing I do need y'all to keep in mind is I am only one person. This exam is written by 4 other people. I can't actually promise that this is the only other kind of question that we ask. I can tell you what we usually ask, but I can't actually promise you that this is the only other thing that we ever ask. But I can go ahead and demonstrate how to count sigma and pi. This is not the answer to the question of what are sigma and pi bonds, but this will at least address what sorts of questions can we do. So sigma and pi bonds come down to the fact that when you talk about single bonds, there's one sigma, which I'm just going to use, and no pi bonds. If you got a double bond, you needed more places to put the electrons. You actually have one of each. And if you have a triple bond, you have one sigma bond and you have 2 pi bonds. And yes, we will hopefully have time to talk about where all of this comes from. So if you just need pi bonds, then what you might notice is we don't care about single bonds and pi bonds. We just care about double bonds and triple bonds. Well, if we're counting pi bonds, all I have to worry about are these guys. So I have 2 pi bonds in the triple bond plus 1 in the double bond, and that is 3, and I'm done. So there are 3 pi bonds. Pi bonds cannot hide from you. Pi bonds have to be drawn in. Pi bonds are definitely the place to start. Now, the other thing, though, that we mentioned are sigma bonds. Somebody else had asked things like, what are the places where, like, what are either like common traps or like easy tricks? I will say this for sigma bonds. And again, we don't have to do this, but from an exam writing standpoint, if it's a multiple choice question on sigma bonds, the smallest answer, this very smallest answer, is wrong. The smallest answer choice is wrong, and I'll show you why. So it's actually a trap I fell in today because I was tired. So basically, when you count sigma bonds, every single bond, every double bond, every triple bond has one sigma bond. So what we usually assume you're going to do is you're going to look at this shape and you're going to go 1, 2, 3, 4, 5, 6, 7, 8. And you're going to tell me that there are 8 sigma bonds. That's the wrong number, but that is the easy number to come across. So 8 sigma bonds is too small. It's too small because there's no hydrogens drawn in here. So that other drawing that we already did that shows where all those hydrogens go, this is the actual structure we need to look at. This thing has, need a different color, that bolds. We'll use purple. Purple's great. Nice bolder. Oh, I guess this is the boldest I get. So this really has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. This actually has 16 sigma bonds because of all the hydrogens. So 16 sigma bonds is correct. I hope. I'm going to look back at my work real quick. It looks good. So usually if the number of sigma bonds is a multiple choice question, I don't know how many will give you. Like, I don't know if the biggest number is the best one or not. that I cannot answer because I don't know what we put on the exam at this juncture, but I can tell you that the smallest one's wrong because it's so easy to just count the number of lines and be like, 8 seems reasonable. So the smallest number is always wrong. The biggest number could be right, could be wrong. I don't promise that one. But the smallest value for sigma bonds is always the wrong answer because it's just so easy to miss one somewhere that the smallest number is always wrong. Um, After that one, I can't promise because maybe because there's too many options, but the very smallest number is always wrong. Um, okay. Oh no. Where did the questions go? There. Okay. Intermolecular forces in boiling. Nope. So skeletal drawing questions. I answered this one. Um, the electron domain shape diagram. Um, so y'all have access to a lot of these. Um, so I have one that I use. But honestly, I had two that I used. So I have this one that I made my class make. And so we spent time putting this thing together. Um, and so this has lots of fun drawings on it. And then the other one, so as far as where you can find it, um, my notes, I stole this from Dr. McCord at UT Austin because I got to watch him teach for a little while as part of a project I was on. And he is his sketches, like he's actually just really good at like cartooning and sketching and things like that. So he's got a very nice like visual organization to things. But here it is in a larger format. You guys also have diagrams from the textbook. I don't know if the lab has its own, but you can find a whole bunch of different formats of Vesper shapes and how they're organized. This is also my favorite because this fits on an 8.5 by 11 piece of paper really nicely. So I personally like this demonstration because it's very easy to try to talk about all of them at once with this particular layout. So that's the other reason why I stole it, but why I try to put his name on it as often as possible because I did not make this. I just admired it. And that's why it's got his name on it because I did not make this, but I like it. Should actually double check and make sure he's still at UT Austin. Anyway, a lovely human. So that's so as far as where you can get this, take a screenshot of it is also an option. Just hanging out in the notes. My notes. I know not everybody has the same notes. There definitely is a thing though. I need at some point all the instructors we need to get together and be like, what is the coolest thing that you have in your notes? Because I know everybody's got something. Because I've definitely stolen stuff from Dr. Diekman, and I've seen Dr. Wong's color coding. Oh, beautiful. Um, Dr. Bacon, I haven't seen as much as her notes. So I know that there's something, or Dr. Hashami, I haven't seen as much of their notes. So I'm sure that there's something else that I would oddball and be like, oh my God, I love that. Um, so there's always something. Okay, I did not really do sigma and pi. But let's actually do percent yields because percent yield is relatively straightforward. Um, so percent yields. First of all, I know it's been a hot minute. Um, So this first question we did with the 5 grams of nitrogen gas and an excess of hydrogen, how much ammonia can be produced in grams? And we calculated this and we got an answer of 6.1 grams. This 6.1 grams, where you have a question all in words, and then you just work the whole thing with math and your calculator, and you're like, what did you get? That is the theoretical yield. So we refer to that number whatever that number is, as the theoretical yield. Theoretical yield. Because you just did it with a pen and paper. I just did it with a pen and paper. So this doesn't take into account like human error. There's nothing about like, did we actually manage to catch everything? Did everything actually react properly? There is nothing but my calculator and a pen and paper. I realize it's digital, but you know what I mean. There's nothing but a calculator to tell me how I got this number. So I can show you all the math, but this is the theoretical yield. This is the yield if everything goes right according to my calculator. That's what the theoretical yield is. My actual yield then is something that has to be given. So I'm going to use this exact same problem again, but set it up as a theoretical yields, a percent yield problem. So it's going to read a little bit differently. If 5.4 grams of ammonia are produced, what is the percent yield? So what's happening here is it told me something about the beginning. So I've got my nitrogen, get my reaction back out here again. So I have my 5 grams of nitrogen and excess of hydrogen, and then it told me how much is produced. Are produced in a lab. Let me add that line. So usually we try to add some line about produced in a lab, or sometimes we'll add names. So sometimes this will be like, I don't have any names right now. Vanita, sorry, she's the person I work with. So I'm like, who am I going to see tomorrow morning? Vanita. So if this said something like, Vanita runs an experiment where she mixes 5 grams of nitrogen gas in an excess of hydrogen, she gets 5.4 grams of ammonia after she completes the reaction. What is the percent yields? So what's missing here then? So missing is the theoretical yields, because this is supposed to be the actual. We have to give you the actual. So we give you the actual. That's the thing I haven't said yet. Because the actual is supposed to be what happened in real life. And on a paper, there is no real life. Everything is fictional. So we have to give you that actual value. So sometimes we'll give you a little story to make it more obvious, but there is the actual. The theoretical, that is that thing where we take the 5 grams of nitrogen, and this is the part where, since it was like the first thing I did in the exam review, I'm going to reproduce this, but really fast. So for those of you that are like, I don't know where this is coming from, that is because I did this like an hour and a half ago. And for every 1 mole of nitrogen, there are 2 moles of ammonia. And for every 1 mole of ammonia, there is 17.034 grams. And that got us the 6.1 grams. Whoa, what is the other mark thing for? That is my theoretical yields. So I can still calculate a theoretical yields. The actual has to be given in the problem, unless you solve for it. So then, but the question is, what's the percent yields? I'll get distracted. So the question is, what is the percent yields? The percent yield is the actual divided by the theoretical times 100%. So actual divided by theoretical times 100% equals 88.5. So that's an example of percent yields. So hopefully that helps with that. So yeah, so we have to either give you the actual yield, unless we give you everything else and ask you to solve for actual yield. That looks a little different. Let's, since I brought it up, let's do that one too. Okay. If a reaction, oh, make this longer. Just something completely different, produces water. And has only a weird number, 42% yields. If actually let's do if the reaction below if you begin with 30 moles of hydrogen gas, what is the actual amount obtained after the reaction is complete? Okay. Oh, I need to give you the reaction. Hydrogen plus oxygen goes to water, but we put a 2 here and a 2 there. Yay! So if the reaction below produces water, it does, and has only a 42% yield. If you begin with 30 moles of hydrogen gas and an excess of oxygen, what is the actual amount obtained after the reaction is complete? Okay, I'm okay with this. So we're still banking on having actual divided by theoretical times 100% to equal percent yields. We have some of this, but we're currently missing both the actual and the theoretical. We're going to solve for the actual, we still need the theoretical yield. We are going to leave this in moles though, in moles. Sorry, I keep changing the question. It's really funny because I have conversations with other people and they're like, making up questions on the fly is a terrible plan. And I'm like, I know, and I do it every single time. Because I didn't think about this one until I was saying we have to give you the actual. And it's like, oh, that's not true. We don't have to. We just have to get creative. So the actual is what we're going to solve for. So the theoretical I still need. But what I do know is I know about this 30 moles of hydrogen gas. So since I know I have 30 moles of hydrogen gas, I still need a theoretical amount of water if it just worked perfectly. So if I've got 30 moles of hydrogen, also I'm just in moles. What you should note is that for every 2 moles of hydrogen, I get 2 moles of water. So this is just a 1-to-1 ratio. So this tells me that I do in fact get 30 moles of water. But that then is my theoretical yields. So the amount that I get with a pen and paper and a calculator, that's my theoretical yields. So in my equation, I'm looking for actual, I now figured out my theoretical and I have percent. So my actual is the thing I'm still solving for. My theoretical is this new number, 30 moles times 100% is equal to, the problem told me, 42. So now I can go ahead and start solving. So my actual divided by 30 is equal to 0.42. So I divided both sides by 100%. And then all I'm going to do is take 30 and multiply by 0.42. So my actual then is 12.6. So as long as we give you enough information, you can solve for actual, but we basically have to call that one out pretty directly. And do notice we have to give you, this part's true, because theoretical yields has three pieces, actual, theoretical, and percent, you have to have enough pieces to calculate the thing. So we can either give you two out of the three, but we have to give you enough numbers to solve because it's got three variables in that equation. So you have to have enough information to get two out of the three so you can solve for the one that's left over. So hopefully that helps with percent yields. Sigma and pi, vapor pressure, intermolecular forces, hybridization, and intermolecular forces. Is everything else intermolecular forces? Just about. Okay, and I have 13 minutes left. Huh. Sounds like it's a good time to ask for questions again to see if there's anything else that I should talk about, because once I start intermolecular forces, that takes up a fair amount of time. So are there any other questions in the chat?
I have one more question currently. It
Okay,
is, do double bonds and triple bonds affect bond angle?
perfect. Okay. Yes, yes, they do. Um, so in general, when we talk about bond angle deviations, so we usually spend a lot of time talking about things like lone pairs, because lone pairs are the things that definitely affect bond angles. So this has three electron domains, is a trigonal planar geometry. That lone pair is going to squish together those hydrogens so that you have a bond angle that is less than 120 degrees. Absolutely. The thing, though, is that the lone pair is more negative than a single bond, but a double bond and a triple bond are also more negative, because a double bond, and we often draw this guy, when you think about it, a double bond has twice as many electrons in it as the single bond does. It's right, there's 4 electrons in a double bond. There's only 2 electrons hanging out in each of the single bonds. So you can absolutely get the same general effect. The difference here, though, is when these guys get closer together, this bond angle in here is still less than 120 degrees, but there was another bond angle that still exists, which is this guy. And that one is actually greater than 120. So whenever you're dealing with double bonds and triple bonds, you have to be careful about your bond angles, because you can absolutely have a bond angle that's greater than 120 because you still have the bond. one of the tricky things when we talk about bond angles is bond angles need bonds, and what I mean by that is you cannot have a bond angle to a lone pair. Bond angle is not a bond to a lone pair. So you have times where you're like, well, technically, isn't there another angle between the lone pair and the bond? There is, but that's not a bond angle. Bond angles are in between bonds only. But yes, double bonds and triple bonds absolutely affect bond angles. Yes, true. Sorry, I'm just kind of looking at all my questions being like, what can I do that's helpful? So I am just going to I'm going to kind of take a look at some of the miscellaneous list of other things that I had in here. Um, so there are some that I grabbed from my class that at this point I'm not certain if we answered or not. But I want to make sure that I do address some of these. So um, does the rule for nitrogen oxygen atom lone pairs for skeletal diagrams extend to the rest of the groups they're in? So what they mean by that is nitrogen gets one lone pair, oxygen gets two lone pairs, and as far as the rest of their families, where did my periodic table go? Yay, I found it. We do assume that that applies to everything else in the same family. So nitrogen getting a lone pair, we also assume that that applies to phosphorus getting a lone pair, to arsenic getting a lone pair, I suppose antimony as well. When we start to get farther down the periodic table, it can get a little bit weirder, but we would assume that oxygen gets two lone pairs in a line skeletal diagram, that sulfur gets two lone pairs in a line skeletal diagram, that selenium gets two lone pairs in a line skeletal diagram. We'd go ahead and assume that for tellurium. I sincerely doubt you would see that, but we would assume that all the things in group 6A in a line skeletal diagram get two lone pairs, that everything in group 5A gets one lone pair for a line skeletal diagram. We would go ahead and make that assumption. So yes. So I did answer that one. So one of the questions I got asked was, what are some traps previous students got caught in and got their answers incorrect? I've been trying to do that as we go along, but I will actually mention one other trap that does happen. So this is actually a molecular geometry trap, which is, here's water. And when we draw water, the molecular geometry should look something like this. But we've been drawing Lewis structures for a really long time. So this also happens. The problem is this thing on the bottom is a Lewis structure. And it is a fine and wonderful Lewis structure. And there is nothing wrong with this as a Lewis structure. But there is basically no shape information here. So the thing is that this bottom Lewis structure down here looks like it gives you shape information when it does not, because that is a Lewis structure. This thing on the top gives you some information about shape. So this should be 109.5 as an ideal bond angle. But when you draw it, sometimes you're like, oh, look, shouldn't this just be linear? And it's not. This thing is bent. So the Lewis structure is fine to draw. There's nothing wrong with drawing a Lewis structure of water that that doesn't have any shape information. But you need to be honest with yourself that there is no shape information here. So again, there's nothing wrong with drawing it like this. It's a lovely Lewis structure, but you still need to be able to say that's got 1, 2, 3, 4 electron domains. So since that thing has 4 electron domains, it has an electron domain geometry that is tetrahedral, and it has a molecular geometry that is bent. Apparently, I can't spell geometry, but that's okay. That is bent. So that is one of the traps I see students fall into, which is that they are doing their best to draw things, but because we're trying to draw correct Lewis structures and then apply shape, sometimes they get caught up in the like, but when I drew it on the page, it looked like it had this shape. Instead of drawing the Lewis structure and saying, cool, how many electron domains do I have? And that number of electron domains off of your Lewis structure will tell you what shape it is. Your drawing is going to be the best you can do, but you've got so much Lewis structure practice under your belt that sometimes your Lewis structure just doesn't have any shape information. So it's just a good thing to keep in mind that your Lewis structures do not naturally have shape information in it. And that's okay. Lewis structures aren't meant for shape. That's part of why we have like the wedges and the dashes and all the other weird things, is to try to demonstrate how we can talk about shape. Some of these questions are about things like, do we need to have the 3D Vesper diagrams memorized along with their names and their angles? Yes, you have to have those things memorized. And I had another thought, but I forgot what it was. Oh, one of the other questions I did see, I don't know where it is in this list, but what we're going to do for bond angles is we're going to either ask you for ideal, which would be things like 109.5, or either we'll do deviations slash non-ideal slash actual. So that's not the word actual. So in the case of water, we would just call that less than 109.5. I know that in the lab, y'all did some stuff that gave you like real numbers for some of those bond angles, and that's lovely. We are just going to do less than 109.5. Sometimes you will see us do something where if this was the thing we actually wanted, the only other thing we can do bond angle wise is we could do something like this, where we give you one moment, please. I'm writing things down. Um, where we give you things to choose from, but notice that what you're choosing from is there's some ideal angles in here, and then there are things that are basically less than the ideal, but they have to be close enough to one of the ideals for you to recognize what it could possibly be. So this is the other thing that we can do, is we can either have you guys just tell us the ideal. We could go ahead and say, is it less than whatever that ideal bond angle is? Or we could do numbers, but then you would have to have answer choices where there's only one correct answer. And you don't have enough information from just either a Lewis structure or a drawing that we drew to say exactly what that bond angle is, but you can pick out of a list because you're choosing the only tetrahedral deviation. And there's only one option on here that is a tetrahedral bond angle, but is shrunk because of the lone pair. So that would be the thing that we could do. Okay, it is 7 o'clock. Because I'm going to make, I do want to see in the chat if there are any other questions so that when I make the follow-up video tomorrow morning, I have that because sometimes I make those kind of early. So are there other questions out of the chat to add to the list?
I do not see any right now, but we can give them like 30 seconds to quickly type anything if they would like.
Great, great. But I will do a follow-up video because I know you guys want intermolecular forces and boiling point and some more on hybridization and sigma and pi bonds and vapor pressure. As we're doing that 30 seconds, a brief reminder that hanging out in the 701 section, you guys have on the course homepage pre-recorded lecture videos. And so you guys can always watch those. They are through Microsoft streams. So you do need to log in with your net ID and password. So I know that there is that extra step to go, but if you just wanted to hear some of these things again, you do have that opportunity in there. So that is another thing you have access to. The other thing I'll remind you, because it seems like I tell somebody this every time, the blank exams from 2024 are also in the 701 section. So I personally didn't copy those over into our section because I'm trying to get y'all used to looking at the 701 section, but you guys do have the 2024 exams in the 701 section to look at whenever you'd like. Okay, anything come in?
I do not see anything else.
Okay. Well, I certainly have enough questions to do some more video stuff tomorrow morning, so I'm not worried about that. I think we'll go ahead and call it here and end it here.
Thank you, everybody, for attending LLC's Gen Chem Study Session 3. As a reminder, our next study session will also be online on December 1st, which is Monday, same time, same location as always. You can find the link either email through Dr. Taylor or it'll be available on our Living Learning Communities link tree as well as on our website when available. So thank you all for attending. If you have any questions, feel free to email us. Otherwise, I hope everyone has a good rest of your evening. And thank you so much, Dr. Taylor.
Absolutely.